Hello, this video is being recorded as a part to fulfill the assignment being given to me as one of the student of the structures and properties of material class. The name of the assignment is the heat resisting alloy assignment, and there will be three topics that should be discussed. The first one is the creep phenomena and the classification, which includes Cobble creep, Nabarro-Herring creep, and power law creep. The second one is the Larson-Miller parameter, and the third one is a heat-resisting alloy microstructure, which include large grain, equiaxial, directional, and single crystal. First one, we need to talk about creep phenomena. What is creep? Creep is a deformation that happens in a material at an elevated temperature when the material is being given a static mechanical stresses. It is a detriment to the material and will decrease its lifetime. There's in the McAllister book, there is a figures that describes the characteristic of the creep phenomena, and this figure can be divided into three parts. The first one is called the primary, or also called as the transient creep. From the curve we can see that the graph is decreasing with respect to time, and that's because there's a increase in resistance to the creep itself, or that can be attributed to the strain hardening phenomena. And the second part is the secondary region. From the curve we can see that the rate is constant, and the slope is linear, and also it has the longest duration between the three regions. This region, the slope happens because of as a result of the balance between strain hardening and recovery. What is recovery? Recovery is the process in which a material becomes softer, thus it's easier to be deformed. And the third region and final one is called a tertiary region. In this final region, the rate is increasing, and it can be observed by looking from the curve that the curve itself is increasing. Okay, after a while, the material will eventually fail, also called as rupture, and the reason of that is because there is a grain boundary separation, a formation of internal crack, and etc. And also we can move to the second curve, the figure 8.30 from the McAllister book. We can see from the figure that the time and stresses, the magnitude of it influence the creep strain and the duration of it happening. The higher in the magnitude the temperature or the stresses are, the more creep strain happening and the less duration it occurred. Okay, so after that we move to the classification of the creep. There will be three classifications that we will talk about. The first one is called the Cobble creep, second one is called the Nabarro-Herring creep, and the third one is called the power law creep. So the first classification of creep. First one is called the Cobble creep. So what is a Cobble creep? It's a form of diffusion creep, or a mechanism for a crystalline solid to deform. It occurred through the diffusion of atoms along the grain boundaries. So it occurred along the grain boundaries. And similar to the second one that we will talk about, the Nabarro-Herring creep, it is dominant at a lower stress level and a higher temperature. Yeah. And we move to the second classification, which is the Nabarro herring creep. Nabarro herring creep is a also like a mechanism for crystalline materials and amorphous materials to deform. It occurred at the low stresses and held at elevated temperatures. The difference between this classification and the previous one is that the diffusion happens through the crystal, and the creep rate is inversely varied with the square of the grain size. And the Nabarro herring creep occurs through lattice diffusion. So we move to the third and the final creep classification, which is the power law creep. So the power law creep, okay, it's very involved in dislocation and diffusion, but particular in dislocation. And the difference between this particular classification and the other two that we have been previously talked about is that this one, it's very present in a high applied stress, and the creep rate, creep strain rate of it is very influenced by the ability of a dislocation or the rate of a dislocation. And because of it, is this creep is also happen at or through dislocation. So we move to the next topic, which is Larson-Miller parameter. So what is Larson-Miller parameter? It is a method of data extrapolation which can fulfill the need for a creep data that cannot be acquired through a basic laboratory test. It is a means to predict lifetime in comparison to the time and the temperature, and it's based from the Arrhenius equation. So the parameter which denoted by m has an equation in terms of temperature and rupture lifetime as the one that's being shown right now, and in which the T is the temperature in the Kelvin, the C is the constant, usually in order of 220, I'm sorry, and the TR is the rupture lifetime and is in hours. And finally, we move to the final topic, which is heat resisting alloy microstructure. Okay, amongst all other factors that influence the creep phenomena, one of which is the grain size. So the theory is the larger the grain size is, the better it is able to resist creep. Why it's happening like this? Because the smaller grain the smaller the grain size is, the easier or more grain boundary will be able to slide, and this the sliding phenomena is the will influence the rate of creep, and which will make it higher. And to combat this, to overcome this, there's been some highly advanced processing techniques which has been developed and utilized. One of which is it's called directional solidification, which produce either highly elongated grains or single crystal components. So what is single crystal components? Is it's a material which has a continuous and unbroken crystal lattice with no grain boundaries. And there's also other type of crystal called equiaxed crystal. This crystal is a crystal that have axes of approximately the same length, and the existence of it is can indicate a phenomena of recrystallization.